Hi again. In the last video, I left my char RNN implementation just about ready for training. The first training thing to do is to make sure we can track the training. For that, I define this empty accumulator list that will store the loss function. Then I sample randomly sequences of text in the training set. I take one less than the sequence length because I want to predict the next letter. If I hadn't, I could have sampled the last 25 letters of the text and there would be nothing to predict. And I decide to sample 50,000 sequences. No special reason, it's just to start. There is a difference between epochs and iterations. An epoch is running over the entire train set, and an iteration is running over a given instance of the train set. That's why I define this second accumulator and this second loop. I take the training samples from the tensor containing the one-hot vectors. A better way to do that would have been to use the PyTorch data loaders. But I think it's easier to understand that way. And then the first thing to do instead of training is to break the loop and verify that the data is in the form I want it to be. After a small parenthesis error correction, I can see that my sample has the shape 1, that's the batch size, 25, that's the sequence length, and 100, that's the one-hot vector size. That's what I wanted to see, so I can now get the sequence I want to predict. It's from the same text, but shifted by 1. The training needs everything to be on the GPU. Then I can send the sample through the network and use the loss function to compare it with the sequence I wanted to predict. I have initialized the hidden states of the vector, so that's done. The rest, loss.backward, and the optimizer things are instructions required by PyTorch to modify the network's weights. I just take the value of the loss and put it in the accumulator to track the progress. Then once the iterations are all finished, I log the average loss for the entire epoch. Now it would be pleasant every now and then to see what the network is doing. So that's what I do with this if statement, print the latest average loss in the terminal every 5 epochs. Now it's finally time to launch the training. Yay! It's a game of patience. It took about 1 minute and 30 seconds just to run over the first epoch. And 2 epochs are definitely not enough. So, I used a previous training session I made some time ago. I left it to train for 75 epochs. That was a bit under 2 hours of training. A good time to clean your apartment. But how do I know the network is trained? A good start is to look at the loss function. Here you see how to save it, and the network's parameters as well. It's possible to save the loss while the network is training by adding save instruction to this last if statement. Or you can go all fancy using TensorBoard and whatnot. Any way you want to do it to see if your loss function looks a bit like that. See how it decreases. And then after a while it keeps on decreasing, but not that fast. That means you can stop training about now. Because you wait the same time, but the increase in the network's quality is less and less. That's how I stopped this last training run at 75 epochs. Let's see how this last run performs in the terminal. First, I import PyTorch and the string library I will need. Then I copy over the network class and the translation functions into the terminal. I can define a couple of parameters: how long are the sequences and how many letters I want to sample. And then I create the network. But look, I'm not training it anymore. I load the network parameters from my previous training run and I set the network to evaluation. Now for the magical part. Here is the prompt. I transform it to 1-hot vectors using the functions. Then I sample letters. I start by initializing the network's hidden state. I take the last 25 letters of the prompt and send them through the network to obtain the predicted 26th letter. Afterwards, I collate this letter to the tensor so that when I predict another letter, the new sequence contains this letter for prediction. Then it's a matter of translating back 1-hot vectors to letters. I take from the second axis of the tensor, which indexes letters. The argmax function returns the position of the maximum, which is great because it's the index in the list of letters. I can then append the letter to the sequence. Now the sequence is a list, and I would rather have it as a string for readability. Here. Well, we definitely have some new letters added to our prompt. Let's try again, but sampling more letters. Oops, I had shown the list instead of the string. Wait a second, please. And that's the nonsensical string of letters that looks like text, but is not really, that I was expecting from a last video. The network is trained. Let's proceed to exuberant exultation. Yay! This is the end of this video. Thanks for watching. See you next time. Or stay for a message from the sponsor of this video. May, I'm the sponsor of this video. Don't jump forward too fast. If you jump forward faster than the escape velocity of the Earth, you are going to fall into the Sun. And if you jump faster than the escape velocity of the Sun, you are going to fall for a very long time. Not to mention the consequences for your starting point if you suddenly accelerate to supersonic speed. So don't do that. Bye now.